X. You have target values Y to regress towards. There's a goal for it. The learning has an objective. Principal component analysis, so-called PCA, is an unsupervised learning approach. We're going to talk about there are different ways of looking at PCA. One is the maximum variance view, the other is the minimum reconstruction view. And the PCA is intimately connected to Gaussians. It assumes that the data has a Gaussian distribution. So if your data is not a Gaussian, you probably need to think about whether PCA is meaningful. PCA is one of the so-called unsupervised dimensionality reduction techniques. Illustrated here is that we have on the top right corner, you have this so-called handwritten digits, these images. A well-known data set, the MNIST digit data set, it's collected from USPS, people's handwriting of addresses. Let's say there are millions such handwritten digits, and you want to get a sense how much variation there is in the data set. How are you going to do it? You can look over one image after another image. That still doesn't give you a statistical variation, the bulk of the data. How can you grasp the distribution of the bulk of the data? Here you will see that now if I have a technique to map each image, if the image is 100 by 100, we have 10,000 dimensions. And if I can map these 10,000 dimensions into a point in a 2D space, 10-dimensional number, reduce it to 2 numbers, then all these million images become million dots on the 2D plane. And that's what humans are good at. Essentially, our vision is flat. We only see the 2D patterns. What's illustrated here is the mapping that, for this digit data set, each image comes with the digit label. Is it about 10? Is it about 0, 1, 2, all the way to 9? And each class is given assigned a different color. So you can see that, for example, 0 is colored red. Red forms a cluster. Green is 3, right? So sort of you can grasp this part is more or less the space of 0. Here, this corresponds to 3. And this orange part is 1, okay? And the cyan is 5. You have some 5 here. Sort of, you already see some similarity why each image is mapped to nearby locations. But all in all, this gives you sense of the data, okay? So, and here, I only have these images. I don't need any, the coloring is for you to see in terms of how images are distributed according to the class. Even without the coloring, I see these dots. That helps me to see the variability contained in the data set. So unsupervised dimensionality reduction is useful as a compact data representation of statistical variations. Secondly, instead of dealing with 10,000 dimensions, if I can just deal with 2 dimensions, whatever machinery, whether it's least square regression or other machine learning approaches, you can speed up computation significantly. The third reason is that we know that adding irrelevant features increases the variance of the model, right, in the bias variance trade-off. Feature selection helps reduce noise and overfitting in learning. If I can achieve the similar performance with much smaller dimensions, my model will have better generalization. The fourth reason is sometimes I have a lot of data, I have some hypothesis, but I don't know how to go about it. I don't know what I'm looking for. In this case, I just want to see what's in there. What dimensions have a lot of variation, what is more or less some minor variation, so probably it's not useful that I can throw away. For such a preliminary, exploratory data analysis, you don't have a goal formulated. Unsupervised dimensionality reduction is also very useful. PCA is the simplest approach in this camp. So before we get started, you can think of some straightforward approaches to dimensionality reduction. You have 10,000 dimensions, you just want 2 dimensions. What would you do? Straightforward, most naive approach. Why don't you just randomly sample 2 dimensions? The problem with that is, at the back of your mind, you might be thinking, if I just randomly select 2 dimensions, I'm not looking at these 10,000 dimensional data I have, right? Not looking at the data and I select that. If I get to look at the data for this specific set of data, can I do something better? The second more advanced thought will be, how about I keep a subset of features with most variability? If a signal, if all the, like in images, each pixel, just each dimension, in this case, each pixel, it just recording the intensity of light. So every pixel lives in the same universe with the same units. In this case, I would think that if at a particular location, the intensity varies a lot, and I have this bulk of data, so that might contain something useful. It helps me differentiate instances, differentiate between instances, okay? So if I do that, if I pick the features of most variability, I pick the first one, and then I seek the second one. What if they're highly correlated? As in the case, you have collected some measurements, your office mate comes in and collected the same measurement, not aware that you have already collected the same measurements. So these 2 feature dimensions are highly correlated, and you only have a budget of selecting, say, k dimensions, and then you're wasting 1 dimension, right? Because these 2, although they both have a high variability, they're redundant. You only need 1 copy. So then, instead of just picking the features to conserve these selected features, maybe you can think of, I can synthesize some virtual features. I have some linear combination of the features. What do you care? If I have 10,000 dimensions, I can take 1 from these 10,000 dimensions. I can also compute a linear combination of these 10,000 features, and that still give me 1 feature. And that might perform better if I can find I can capture the most correlation among these dimensions. Okay. So then in this, the idea will be, if I get to select in a set of synthesized linear combinations of features, I select 1, in order not to select another highly correlated feature, somehow I need to look for things with dimensions, the virtual features of some fresh variability, something that has not been captured in the first virtual feature I select. That is sort of the idea of PCA, okay? PCA essentially finds orthogonal directions that capture the largest amount of variance in the data. It assumes that those directions with less variations contain less information and may be discarded without introducing too much error. If you have a bunch of measurements, if some measurement doesn't change much, you can think of, the entire data set is just same value. That cannot be very informative. You just throw it away, okay? So in a way, it treats every variation as useful signal. This is my cartoon version of PCA. It's very simple, but it has every machinery you're going to learn in terms of all the math. But the idea is there. Think about a sender-receiver communication system, okay? You have someone collecting the data. That person is sender. Let's give it a personal touch. Call him Sam. And you have receiver, again, how about Rick? Okay. R for Rick. Okay. So Sam is collecting a lot of data. He's busy working in the field, okay, with a lot of data. And Rick is there, Sam gets the data and sends the data over through this communication system, and Rick receives this, okay? And at each time instance t, you have d numbers sent over in this communication system. So this has been going on for a while, and this is t equals 1, this t equals 2, t equals 3, all the time up to some time t. And the Rick, he's not collecting data. He's not that busy. He's looking at these data and start thinking. He's thinking, what can I do, right? Maybe because the bandwidth is limited, sometimes the reception quality is bad. Maybe Sam doesn't need to send all these d-dimensional data over. Can he send a small bit over if we have some protocol between us? Okay, so that's a question. Can I send only k numbers instead of d numbers at each time instance t? Yeah. Okay. So that's what Rick is thinking. See, Rick is looking at the data. So he thought the simplest case. What if all the past time from t1 to all the way up to time t, in this 2D case, d equals 2, Sam has been sending over same number all the time. Every time instance is the same data. So what would Rick propose? Rick says, let's stop it. There's no point sending over the same data over and over again. Okay? You don't need to send me anything because the data is not changing. Why bother, right? So that's the idea. Rick has this aha moment, right? Said, why not store the mean of the historical data we already have, just to get a little bit of a measurement noise. And Sam doesn't need to send over anything, send nothing. 0, this is 0 bit. Earlier you need to send the d numbers over, now it's 0 number, huge reduction. But things like that's almost useless, right? Constant data. Let's build up the complexity. What if it's decorrelated data? Again, use 2D as illustration. You have x1 and x2, only 2 numbers. Rick, look at all the data, historical data. Each point is is 2 numbers at a time instance. And he look at it that there's no correlation between x1, x2. What does that mean, correlation? It means if x1 takes a particular value, this value, x2 really can be anything. It doesn't, if the data is like that, right? That means if x1 is increasing in its value, the chances are x2 is going to increase the value. But because it's kind of this horizontal, that means x1 certain value, I cannot predict x2 is going to increase or decrease. There's no correlation whatsoever. Okay? So if the data decorrelated, what do? Let's say in the 2D case, right? Let's consider this 2D case. The original D is 2, and then the communication bandwidth is very poor. You can only send one number over at each instance. Which feature would you choose? X1 or X2? X1, right? Because X1 has a lot of variation. So if I throw away X2, that means I'm essentially only I have data, just keep this. This will be, instead of X1, X2, I'm essentially sending over X1 and a 0, right? I knock the second dimension all the way to 0. I assume it's 0. I'm gonna lose something, but what can I do? The bandwidth is limited. Okay, so essentially I knock off all the variation in the second dimension to 0. I squeeze them to 0, no variation, which is 0, constant. Okay, so that will be, you look at historical data and you calculate the variance in each dimension, and you pick the dimension with the largest variance. Okay, and you find the indices and you pick the top K features. Okay. Now, in a very general case, you have this kind of data. Okay. They are highly correlated. You can see this. As X1 increases, I can predict X2 is going to decrease in its value. There's high correlation. At this point, you probably already know what we are going to do, right? We have seen this trick over and over. In terms of following what the intuition we give, what are the possible approaches? How can we build up the complexity? Instead of selecting one of the features, when the features are decorrelated, I don't restrict myself to these actual feature dimensions. I can use those synthesized features. And if I look at this, I say, this looks like elongated, distributed in an elongated oval. And this dimension seems like have the largest variation, right? So if I can pick, I synthesize a linear feature in this dimension, I squeeze, I knock off the variation in this dimension. So essentially, if this is my new dimension, x1 prime, this is x2 prime, I'm gonna squash all this variation to this line. So instead of, if I send x prime, x2 prime, this is equivalent because it's just a linear transformation of x1, x2, just a change of coordinates. But since x2 has a minimum variance in this dimension, instead of sending this, I'm going to send x1 prime and a 0. Okay? So that's the thing. My data were generated using this Gaussian blob, outlined with this light gray. Based on these data, I can calculate this so-called major axis variation and a minor axis of variation slightly offset because I only have limited data. And finding these two axes, and then I'm going to use these two to do my coordinate transform. In this newly transformed coordinates, I have this. I come back to the second scenario I have dealt with, this decorrelated data case. And in that case, I'm going to choose the axis of major variation. So that is, really what PCA does. Essentially, you look at the data, you decorrelate, calculate the variance, and pick the maximum variance, okay? And then you just send a transformed feature over, okay? Yes?
So do we always assume PCA that the interaction
PCA, the mechanism PCA, is intimately connected to Gaussian. It assumes if your data is Gaussian distributed, you are really picking up the major minor axis variation. If they are not, then they don't mean, you know, what you think they're doing. I will show an example later. Yeah. So this is the basic ideas of PCA. You have original D measurements through some mechanism. You encode it into K numbers, Y1 to YK. You send this over in the communication channel. Sam sends over, Rick receives it, and from those K numbers, it's able to reconstruct the original data, okay? And because of that, you know, the thing that's transmitted in the communication network is much less, okay? So we are achieving dimensionality reduction. The things to remember about PCA is that it compresses data based on the statistical distribution of the data. It's optimal also in the statistical sense. It's not like you have a number, you say, can I round it off? It's not about that. It's not a per number. It's through the bulk of the data, over the bulk of data, I'm able to send less, yet, you know, statistically, I'm not losing much variation, okay? The statistical mean where the data is located is irrelevant, okay? Just in the first case, if the data is constant, you don't need to send anything. Just store the mean. The statistical variance, how wide the data spreads, in which directions, this is what's relevant. If the features decorrelated, PCA amounts to feature selection, selecting the dimension of maximum variance. If they're correlated, they find the decorrelating axis and project data onto them. Then you obtain a decorrelated representation, and then you go to previous step, okay? PCA is a linear encoder-decoder because this going from X to Y or Y to X is a linear transformation. With deep learning, you are able to extend it to nonlinear domains, but the concept is the same. The next few slides, we are talking about the math machinery to capture these computational steps, okay? Step one, mean is irrelevant. We need to center the data. Same notation as before. If I have data X, each is column vector, I store it in a row, transpose version. Each row is a sample. N points, D dimensions. This is N by D. We assume it's zero mean. I calculate the mean. We assume this is zero. This is superfluous variation. If it's not zero, we do a transformation. We calculate the mean and let each instance subtract. We subtract the mean from each instance, and now it will be zero mean. Okay? So from now, we assume the data, the X is already zero mean. Okay, it's centered. Step two, we need to find the projection axis of max variation. So this is original data, X1 and X2. When I project these points to their axis, essentially, each point is X1, X2. And this is just the projection of the 2D point to this X1 axis or X2 axis, right? So if you look at this, all the points on the x-axis, you can calculate the histogram. This corresponds to this. You can see the spread. And you can see this side is spread out a little more. That corresponds to the thicker line. This is a histogram of these, okay? This tells you, you see here is densely populated. It corresponds to this peak, sort of around 0.8, because this is where this point is. it's this spread, or alternatively, you have this spread is correspond to this thicker line. If I find that this axis and this axis, this x1 prime, x2 prime, in the new coordinate system, this is x1 prime and this x2 prime. Now the same point, it's just a linear transformation, just a coordinate transform rotation. And then if I look at the projection, you see this is much wider and this is much narrower, right? This corresponds to the first one, corresponds to this curve. The second one corresponds to this thicker curve. Okay, you can see that this curve, the thin green line spread out most widest. So that's the one we are looking for. So how do we numerically capture, quantify this? First, we need to figure out the projection, and then we have to calculate the variance. Consider a point x1, and we have an axis. This axis, this is just a line. This direction is v, okay? And x1 will project onto this point. Let's say v is a union norm, okay? Union norm vector. So the projection of x1, the size of projection along this line is the dot product between these two, right? Because this corresponds to the x1's norm times v's norm times the cosine x1 and v. Okay, this is 1, so it cancels out. So this is this is theta, this is cosine theta. So this length x1 norm cosine theta becomes the size of this. So this is the size of projection. It's a dot product between the x and the v. We assume the data is already centered, okay? Now, this just gives you a scalar, one number. What's the size of projection? But what's this x hat? The approximation of this point on this line. If I have to find it, we have talked about least square, right? This is a perpendicular orthogonal projection. You can link this point to any point on this line. This point has a shortest distance, right? This point will be the size of projection times this directional vector. So essentially it's pi times v, and that is just that. Okay, very simple math. So far so good, yes? Now let's calculate this point P, okay? What is the mean and the variance? The mean of the projection size, the scalar, this one number, we can estimate it with a sample mean, xi times v, and since v is a constant vector, we can take it out. And this is the mean of the sample, so that becomes 0, okay? The variance of that, because the EP is 0, the definition is P minus EP, E of that, right? Definition, because this is 0, so I can simply calculate the pi square. You should have 1 over m, but I make it a proportional since n is a constant. And this will be, xi transpose v squared. And this thing can be written as, in matrix form, it's just the quadratic form over the data matrix, okay? Now, our idea of seeking the maximum variance of that, we want this to be maximum. We want to find the v. Every v, you can calculate v of p. We want to find the v that gives the largest v variance. So it will be finding the maximum variance, any direction parameterized by this vector v of unit length, and we substitute this quadratic form, and this term can be written. Usually, we don't like this constraint, so we can, it's just a one scalar constraint, so we just introduce this ratio. So if v is some scaled version, let's say if v is v0, let's say have unit norm. If it's any scaled version, so v0 transpose x1 x v0 is what I want to calculate. That's my v of p, okay? But instead of using v0, I actually have v. Then if you calculate this, this will be s times v0, s transpose x, and s v0. But in the bottom, I also have s v0 transpose and s v0. So these s all cancel out, and v0 transpose v0 is 1. So this equals exactly this. So these objectives are identical, okay? That's just a trick. If you want to seek directional projection with unit length vector parameterization, you can get rid of these constraints, letting the projection be parameterized by any vector in that direction, but you make sure the criterion is the variance divided by the, over the magnitude squared version of this vector, okay? So how do we solve this? One way of looking at this is, I want to maximize this subject to this, okay? And we introduce the Lagrangian, and this is dual variable. We put this into this criterion, we turn this into unconstrained problem. Lagrangian. Then, if for the optimal solution to this constrained problem, it must satisfy this necessary condition. The gradient at the optimal solution has to be 0. So if we find the derivative of L with respect to V, we have this. It's just the quadratic form. You do the differentiation, it's the linear term here. Likewise, for this, you have 2s v star. And this has to be 0. It has to satisfy this. And then we can derive x transpose x v star must equal s v star. And that just says v star, the optimal solution, has to be the largest eigenvector of x transpose x with eigenvalue s. Okay, s is eigenvalue, v star has to be an eigenvector. Because we are, so the largest eigenvalue is that, so first this establishes this eigenvector. So how do we know we want the maximum eigenvalue, not the minimum eigenvalue? If we go for the objective v transpose x v, if this equals sv, on the optimal we have this. If this equals sv star, then the objective value becomes s times v star, and that we know is 1, so this equals s. The objective value is s. Since we are maximizing this, we have to seek the largest eigenvector, meaning the eigenvector with the corresponding eigenvalue that is largest. Okay, this shows this. The eigenvalue is the objective value. So that just gives us the first PCA, first direction of maximum variance. How do you pick the second one? Let's say we have picked the first one. It has this property, okay? Now, the residual after subtracting the first k minus 1 projection is, this is my original x. And I'm going to project every point. So this is x1 transpose, xn transpose, vj, okay? Each point project to this. This is my size of projection. But I need to figure out the representation, the vector itself, not just the size. So I need to do the vj transpose. That's just the v thing we're talking about, okay? It's just in the matrix form. So that's why it's this form. X minus this is that I pick the first projection. I have all the components living in that space. I peel that off, okay? So that's the residue. Now the k, the principal component, is orthogonal to existing directions, yet it captures most of the variance in the residue. I have already used k minus 1 directions to synthesize x, okay? And this is the remaining thing, the information I have not captured. So among this, I want to pick the direction of maximum variance, but it has to be orthogonal to the previous one. Otherwise, there's correlation among them. So that intuition is captured by, instead of dealing with x, original x, I'm dealing with the residual delta x transpose, just in the same spirit of this variance calculation. I also require the new direction to be found is perpendicular to any of the previous directions, okay? So far, we have figured out the first one. We are doing this induction. Find first one, we can use this recursive formulation to find the second one, okay? Now, the thing here is that since delta x is x minus sigma x vj transpose, and when I do the x vj transpose, when I do the delta, this is delta x transpose delta x equals this. So you can think of, I have the first term, second term, transpose, this transpose. And then there's a cross term. Okay. If you look at it here, sorry, there's a v, sorry, this is much simpler than this because the v is orthogonal to vj. So when you do delta x times v, sorry, it's this x minus sigma x vj transpose times v. This will be xv minus sigma x vj transpose v. This j is from 1 to k minus 1. All of this will be 0, right? Because they're orthogonal. So this whole term will be 0. So delta xv is simply xv. Oh, it doesn't. I can't get rid of this. That's nice. Okay, so essentially delta xv is simply xv, okay? Because of this constraint, v is perpendicular to this. So now the kth principal component is essentially solving this this criterion with this constraint. That is a view, is kind of recursively calculating PCA. You find the maximum axis of the projection, project the data to it, you peel it off, onion peeling. Look at the residue, you find the second direction. QR decomposition. The X equals QR. Why do you make that connection? Oh, right. In recursion, yes, you always, similar ideas, they always find the first one and then the second one orthogonal to it. That idea is recurrent. But yeah. But we do use QR decomposition to find eigenvectors. In the end, it becomes eigensolutions. So in a way, there is a good connection. But we can also understand the definition of finding multiple PCAs as this one-step joint space search problem. Basically, the first k principal components capture most of the variance in a k-dimensional subspace. We can do it one by one, reduce the dimension one by one, or we can think of, if I have to find a 2 PCA for the 3D points, I'm just seeking, if k equals 2, find any plane, right? Find any plane I can project all the 3D points onto this plane. And that gives me this scatter plot in the 2D view. And I can calculate the variance of these 2D points. The 2 PCA for these 3D points can be understood. You can give any slanted 2D plane, and you get this, and you calculate the total variance. And the PCA will be the 2 PCA, the first 2 PCA correspond to the subspace, gives you the maximum variance. So you're seeking this jointly, okay? And these, in terms of math, they're equivalent, okay? Both views are equivalent, but it's good to have. Instead of just think that the PCA is defined successively. No, they can equally understood. If you don't just seek one line, you project one line. Instead of one line, you project it to a subspace, a 2D plane or 3D hyperplane. And in that projected subspace, you can calculate the variance. That variance is maximum for the PCA subspace, okay? So how do we have the solution for the first PCA? How do we solve the kth PCA? Let's do the proof by induction. We already know the first PCA is the largest eigenvector of X transpose X, that's the feature covariance matrix. That assumption is true, okay, for k equals 1. Now, the problem we need to solve is maximize this criterion. We need to find a new V. This V is perpendicular to all the previous PCAs. And again, we form the Lagrangian, and we have the objective, and this is the union norm constraints, and this is the orthogonality constraints. For each constraint, we introduce a dual variable. This is S, this is for each of this, we have a TJ, okay? And the necessary optimality condition is that the gradient of this, partial L, partial V star, has to be 0. And we do the derivative. You have this, we have seen this before, and this is just with respect to V, this is a linear function, it's just this. V is a variable, the rest is just constant. And now we multiply both sides, this equation, we multiply both sides by Vj or Vm, just to let the notation not clash with this summation here. This m taken from one of the k eigenvectors, the PCAs. if we multiply by this, sorry, missing a transpose, then we will have this V, multiply here, and this. And let's look at this term first. M is one of these K's. Only when J equals M, you get a VM transpose VM, that's 1. Any other J is going to be 0, right? We assume they are orthogonal to each other. So only one term survived from this summation. And this one, we know the next direction we are seeking is orthogonal to any of these K directions. So this will be 0, yes? So now we have this. But this one, we're going to write it using the transpose version of that. So we do the transpose, and then the inside has to transpose again. So X transpose, X, and the VM, okay? Now, this looks, we know VM is previous, we know they are eigenvectors. It's eigenvector of this covariance matrix. That has to equal to some eigenvector of VM, okay? So we are substituting that. So, okay, and then it becomes clear, VM transpose V star, we know that V star will have to be orthogonal to it, so this becomes 0. So in the end, it becomes Tm, and we know the optimality conditions that this will be 0, so Tm has to be 0, okay? So now we know this, on the optimal solution, the T, all T is 0. So this has to be 0. So this term has to be 0. So that gives us this. Okay? This just suggests a V star. The next direction is also an eigenvector of the covariance matrix. And it is also orthogonal to all the previous directions. Okay? Now, is it guaranteed that all the eigenvectors are orthogonal to each other? The answer is yes, for real symmetrical matrices. There's a spectral theory in algebra, linear algebra, it's called related to Rayleigh quotient optimization. PCA essentially is maximize this function, and this is considered Rayleigh quotient. Rayleigh quotient is defined by if M is a D by D real symmetric matrix, the quadratic form of this divided by the norm of the V, that's called a Rayleigh quotient, okay? And we have a way to solve this. I'm going to have an alternative solution to what we have, because PCA is just a special case of the Rayleigh quotient optimization. Consider M's eigendecomposition. This just shows that eigenvalues are ordered, and this is just definition of the eigenvector. And this is the eigenspace. We know this is orthonormal, all eigenvectors are orthonormal. We know this using eigenvectors, we can, as a coordinate transformation, we can diagonalize M, right? Because MV equals lambda V, so M, this is a per column. If you write it into a matrix, it will be V times this lambda, okay? And then V is orthonormal matrix. You can do V transpose on both sides, and this will equals lambda. So you can diagonalize matrix using the eigenvectors, okay? So now Rayleigh quotient, if we can represent this value in terms of the matrix eigenspace. Any vector V can be represented as a linear combination in the eigenvector representation, right? It's again, this is D axis, and they're orthonormal to each other. It's a proper coordinate system, so you can always represent any vector using that basis, and that coefficient is alpha, for example. It's just a notation. If the V has a union norm, that means you just V alpha times V alpha has to equal 1. And that will give you, since equals 1, and this is I, this is orthonormal, so you have alpha transpose alpha equals 1. And write it out in the equation format. It says alpha squared sum up to be 1. So you can understand the alpha squared version is weights, is a linear combination weights, is a convex combination weights. They have to sum up to be 1. And the Rayleigh quotient, on the other hand, we have this change of basis using alpha. So we get this, and this we have seen in the before can diagonalize m, becomes lambda. So this becomes a much simplified form. Essentially, it's just lambda j alpha j squared. So these two taken together, in the m's eigenspace representation, the Rayleigh quotient becomes a linear combination of the eigenvalues. Very simple. Okay? Now, you have non-negative, you have this non-negative lambda j, alpha j squared is all non-negative, right? You have all these combinations, linear combination, the whole thing sum up to be 1. What's the maximum? You have to, all the x have this weight sum up to be 1. And these lambda ordered from lambda 1 to lambda d. You put all the mass on the first one, you will get the largest value. If it's not, if you don't put all the mass on the first one, you have something else. Essentially, you have some portion of lambda 1 times 1 minus t, something that's less. And this is bound to be less than, putting everything, putting the 1 over lambda 1, and the rest is all 0, right? That's just the nature of the weighted average. Weighted average, if you are seeking the weighted average cannot be more than the maximum of all the numbers, right? And it will always be more than the lowest number, right? That's just what it is. So projection to the largest eigenvector of m maximize the Rayleigh quotient. Likewise, if you project to the smallest eigenvector, that minimizes the Rayleigh quotient. And this whole thing can be extended to a subspace of k bases. And the Rayleigh quotient is essentially summation of the first few terms. And the largest can be achieved if you take the first k leading eigenvectors. That gives you the maximum value. It's just summation of the first eigenvalues. Or if you want to minimize it, you take the last k eigenvectors, okay? So let's apply this to PCA. PCA is just, in this case, it's a Rayleigh quotient with X transpose X, the feature covariant matrix, as the Rayleigh quotient matrix M. And if X has this USV transpose SVD, the covariance has VS square V transpose. We have seen plenty, okay? So the PCA essentially is this Rayleigh quotient, and the first solution is essentially taking the first eigenvector, the value is just S1 squared. If you are looking for K PCAs, you are looking at the K eigenvectors, and the value is the summation of the first K numbers. Any questions? Eigendecomposition. Data X is n by d, number of instances times number of features. We have already pointed out these two highly correlated matrices. One is a covariance matrix, X transpose X. Its number of instances is the same. Sometimes we call instance, so it's the features, number of features times is d by d. Okay, it's a feature similarity. Grand matrix is the number of instance times is n by n. Okay, sort of this is indicating the Gij is instance similarity, Cij is the feature similarity. They all have X, C, and G, they all have the same left or right eigenvectors. Essentially, if X is USV, this is just SVD, S is diagonal matrix, C is V S square V transpose, G is U S square U transpose. So V would be X transpose U S inverse. So the consequence of this is the following. I'll get to that. If you have 1,000,000 instances, but D is small, 10 or 100 or something, you just calculate the eigenvectors of covariance as we have derived, because the C matrix is D by D. If you have 100 features, you're only solving the eigenvector of 100 by 100, very small matrix. You just calculate this, small matrix eigendecomposition problem. But what if you have, 100,000 dimensions? Okay, then probably 1,000,000 features, and probably that's not a good idea to calculate the C. So what do? Either you look for the SVDs. The first SVDS is only solving the K, is only solving, this will give you X equals U1 all the way to K, and S 1 to K, and a V 1 to K, okay? It will return this, only the first few eigenvectors, and you can take the right singular values, the singular vectors, and that will be your PCA. It's much more efficient to solve. Alternatively, you can calculate the eigenvectors of the gram matrix if that turns out to be smaller. So you can calculate the U, because once you have the U, right? Because S equals U SV transpose. If you know the U, you certainly have X, and this also gives you the S. When you solve this, you know S squared, so you will know S. Then V transpose will simply, becomes X. You just step by step inverse U transpose and S inverse, and then take this transpose to get to the V. So that becomes this equation. Okay? Basically, U and a V, they always come in pairs. When the D is small, go for the covariance matrix, solve for the V. Or you can solve U and derive V through X. Okay? That's what it is. Now, the first step, we center the data. The second step, we find the projection axis of major variations. The third step is to reconstruct the data. Okay? So, X, you have the SVD. You find the covariance. Through this, you find the projection axis. And this is calculating the projection coefficients, the size of projection. Again, the X is X1 transpose, Xn transpose. When you have the V1, Vk, when you do this times this, it's give you the projection size on each axis. So that's give you, the dimension is m times k. Now, my original X has m times d. When I do the projection, I have n times k. Each instance can be represented by k numbers. When Rick received these k numbers, he has to be able to reconstruct an approximate version of the original X. How does he reconstruct? Essentially, it's this X project to V. You transform the size of this P, right? This is X, this is V, you have X transpose V. What is the approximation? It's just this point. So this P times V. That would be my hat, X hat, right? So this is what it is. Y, essentially each is the y1 to yk. Okay, so this is yn. So, sorry, this is the first element, this is the kth element, this is the nth instance k coordinates. And on this side is initially is a v1, this axis, but I need to reconstruct with this. I'm going to do v1 transpose, v2 transpose, vk transpose. So this times this is the k coordinates along each of these k axes. I sum them up. That would give me the x hat, the reconstruction. So far so good? Okay. Now let's analyze the reconstruction error. We have x. We already found our v. We find this is the projection size and this is the hat, the prediction. The reconstruction error is this. How much do we lose? It's each xi minus this, the approximation lies in this subspace, the PCA subspace. And this essentially is put in this equation, essentially becomes this, okay? Very important insight here is that the PCA, the reconstruction error, I can expand it, and this is a idempotent orthogonal projection we have seen many times when we do the least square. It has this property, right? Any power equals P itself. Once you project into that space, you project again, it stays in that space. So this twice is just by itself. And then if you write it out, it becomes xi transpose xi and xi transpose vv transpose xi. And then we write it out, you can see this term, the first term, has nothing to do with v. This term, this is pi, the size of projection. So it's pi squared. This is summing up all the projection size. That's just the variance on the projected axis. That's the PCA's variance criteria we proposed at the very beginning. This data variance has nothing to do with V, and this is the variance on the projection. So this is a constant, and this is something initially we want to maximize. So if we minimize this, we essentially maximize this, right? Because they are held together by the constant, which means that minimizing reconstruction error is equivalent to maximizing the projection variance. The math says so, and it's even more intuitive just looking at the graph. You have a point, you have this orthogonal projection, and what it says is reconstruction error, plus this equals this hypotenuse, right? Because it's orthogonal, right? So if this is constant, if this is constant, if this is minimum, this has to be the maximum. Likewise, if you find things that spread out along this axis, the reconstruction error has to be the smallest. Okay? The criteria is collecting all these errors over all the points. So you have to have trade-off among all the points. But for each term, you have this duality. You have this constant. These two sum up to be the same constant. So the whole criteria has this duality. So this provides two dual views to PCA. You can understand it. It's easier to understand. When we propose it, we say maximum variance. But you can also understand it, find a projection, find a subscript projection, so that the reconstruction area is the smallest. So some of you have already been thinking about the TLS we talked about last time. We don't talk one after another without reason. They're all connected. If X is USV transpose, in PCA we find the projection as the first k, X projected onto this first k eigenvectors. X hat is using the projection coefficients to reconstruct using the basis. And essentially we have this. And we can write X, we can expand it using its SVD. And this just copy over. This just denotes the first k. This is just V1, VK, okay? And this times this, the first, it will be 1, 1, 1 for K1, and the rest is 0 because the VK plus 1 all the way to D will be orthogonal to V1 and K, right? They're orthonormal. And then S times this, essentially the only thing survive is S1 to SK, right? So this just becomes this thing. And because this is 0, I can expand it V1 to K all the way to V. The effect is the same because it will as if they're not existent. Now, if we look at the solution, the PCA reconstruction essentially is a U and a V with first K components preserved, all the rest knocked out. This is just our Eckhart-Young theorem on the low rank approximation to X, right? It's identical. So PCA is equivalent to TLS. And if you think about it, it is seeking the projection subspace. The V thing, it's the space to generate the data. Last lecture, we have a question. Why in LS, we are looking for the, first few, related to the dominant eigenvalues. Why the TLS is looking for the smallest one? Because the way they parameterize is different. In PCA and TLS, it's seeking the projection subspace. While in least square, it's seeking the normal direction to the projection subspace. Why is that? Look at this criteria. In the joint space, I can write it as XY, joint space, times V. V is W and minus 1. Yes? I want to minimize this. Essentially, in the data space, I have some 2D points. In the 2D example, I essentially X, Y, each is just a point in 2D. Okay? And this is just a linear function. I want to find the line. The V is my normal direction to this line. Yeah? The V has to be normal. Oh, yeah. This times this equals 0. Ideally, it should be 0, right? So V is the normal direction to this line. While in the PCA, it's the projection subspace. It's something you use to predict your data. That's why they are dual to each other. They complement to each other. Okay. In a 2D case, according to the Rayleigh quotient, optimization. In the 2D point case, X is just 1D, Y is another dimension. What's the best solution to this V? It will be the minimum, the smallest eigenvector, right? Right? It's minimizing this. You will find the least square, the least eigenvector V2, and then you will scale this last component accordingly and get your W. So this should remind you how they are different. OLS is this solution. This is essentially taken from PCA's point of view. You are looking for the orthogonal projection. You are trying to minimize the orthogonal projection distance. Last time we give you the result without telling you why, and this is why. Okay? Through the connection to PCA. Okay. Any questions? Yes? Say that again, is OLS and TLS? Oh, which one's where? So what's the assumption of OLS? There's no noise in X. What is the assumption of TLS? There's noise in X. So you have to decide which assumption fits your application scenario better. If you believe X has no noise, go for OLS for sure. If you think that there's a same amount of noise in X just as in Y, you should go for TLS. Yes. Okay, that's good. The question is, you have PCA, TLS equivalence. If PCA has this Gaussian assumption, so does TLS. Same restriction applies. So maybe it's good for me to show, if the data is actually not Gaussian distributed, okay? But before that, I want to see if there are any other questions on the material we covered so far. Oh, yeah, there's one more question.
Yeah, it seems that there's no noise coming, right? We have no prior coming.
We assume no noise in W.
Like we don't have a prior.
That's right. That's right. Yeah. That's why last time we only made connection to OLS, right? We are not making connection to ridge. Okay. So PCA on Gaussian distributed data, okay? If data like this, you have major axis and a minor axis. This is what PCA will find. Oh, sorry. PCA will find these two axes, okay? You calculate, you get the data, you calculate the eigenvector of this. This is the first one. This is the second one, okay? But if the data is sinusoidal, it's not a Gaussian. This is what I get. This is the example I chose, and I calculated this will be V1 and this will be V2. Now the question is, I have this data. If I use the first PCA to compress data, what will I get? So all these points, these will be represented by these points, right? I squash all the variation in this direction, right? And the question is that a good representation? No, it's not. Yeah. If it's a multivariate Gaussian, if it's a 2D Gaussian, you project, you can already see each axis is still a Gaussian. The marginal distribution also Gaussian, and you can pick out this major axis and the minor axis. And in the general Gaussian representation, you have this PDF. If you have constant features, essentially sigma is 0, right? In the decorrelated features, sigma is a diagonal matrix. That means that all the off-diagonal cross, the covariance between two different features will be 0. What does that mean by decorrelation? Decorrelation means there are no linear relations exist. Let's prove that. If there is a linear slope, if xj is linearly correlated with xi plus some noise, and we assume that it's 0 mean, 0 noise, mean noise, and it's a non-trivial xi variation. And then if you calculate the covariance, essentially becomes the xi xj, and you substitute this assume the linear relation into it, and then you will get SEXI, and XI and N, they are independent of each other, and EN is 0, so that term is cancelled out. So it only remains this. So if the covariance is 0, and this is non-trivial, it contains non-trivial variation, S has to be 0. That means decorrelation. No linear relation possible. But it doesn't mean that it has no other relationships. It could have nonlinear relationships, but definitely there's no linear relationships. Okay? When there are correlated features, so sigma is a greater than 0, is a PCSD. It's a symmetrical matrix by definition. There always exists an orthonormal transformation. Basically, it's this eigenvectors that can decorrelate all the features. Just like in the Rayleigh quotient, you use eigenvector to diagonalize the matrix. Once you're diagonal, meaning the transformed version has no correlation between features. So I want to explain the distinction between decorrelation and independence. Decorrelation just means that the covariance between two variables is 0. Independence is a much stronger assumption. It says the joint probability is a product of individual probabilities. Independence implies decorrelation. If they're independent, the covariance is bound to be 0. You can prove that. But decorrelation does not mean they're independent. Okay? For Gaussian though, because the Gaussians are determined by the first two moments only, the mean and variance, covariance, decorrelation is equivalent to independence. And you can see that in if all the covariance is 0, so the form of this in the 2D case is just that. And that you can written as the individual, the PDF can be decomposed as a product of the 1D PDFs. If I have data like that, okay, PCA will give you, essentially it's fitting it as it assumes, it doesn't know that, right? Assume it's a Gaussian distributed data. It's essentially fitting this ellipse. And it will pick out this as a V1 and this as a V2. But somehow we look at it and say, it wouldn't be nice if I can pick out, these two components, right? This is called ICA, independent component analysis. This is trying to go for this decomposition. Okay? There's a nonlinear solution for that. It says the data, when I observe the data, is a mixture of these components. I can unmix these two components. Okay, so there is this distinction. So always think about PCA. When you think about PCA, you are essentially treating this data as a Gaussian blob. There's some directions you have more variation, some direction you don't have as much. This gives me cue. We'll talk about this last thing about we always talk about all the models with respect to probabilistic view. PCA, so far, there's no probabilistic view. We have to put it in a larger family in order to give it a probabilistic view. See you next time.